Hello, everyone. Thanks for coming to the talk. I'm happy to share this joint work with UTSC and Alibaba Cloud, both in China. Unfortunately, our authors are not able to get visa in time to attend. That's the reason I'm giving the presentation here. Okay. So nowadays, we have more and more database applications running directly on cloud using cloud-native databases. And actually, many big tech companies have started offering native database products, such as Amazon Aurora and PilotDB from Alibaba. These are databases that are designed and built for cloud infrastructures, and they allow one to actually pay for the actual resources used. And a trend within this trend is to have resource disaggregation, where we view these individual resources, for example, CPU, DRAM, and storage, as layers of resources where an application can freely and independently grow or shrink the actual resources at different layers based on its actual need. And all these layers are connected by fast interconnect. So the cloud-native DB will have large data access needs, right? So we want the storage capacity to be large and elastic, and we want to have large and fast buffer pool for our reads and writes, and also we want persistence and we want them fast. At the same time, cost effectiveness is always a big concern for industry. So one concern here for DRAM as the memory layer is that it is actually quite expensive, and also it has a lower density per server because a certain DIMM slot cannot support very large memory. And finally, it is volatile. So a good news with recent PM offering is that we actually have a product that seems to have the all-around capability to satisfy our needs for these cloud-native databases. It has a performance much closer to DRAM, yet it is still significantly cheaper. It has high density. For example, a certain DIMM slot can support 4 times as much PM as DRAM, allowing a single and expensive server to support more compute nodes requests. And finally, it is non-volatile, which means we can actually do fast persistence. What this allows is just for us to have compute nodes running the database transactions, queries, etc., to actually have very small DRAM buffers, right? For example, like 10 gigabytes. And then we have larger PM nodes, right? That has much larger PM buffers to help us cache pages as well as persist the logs. And the implication of this is twofold. First, we allow these compute nodes to have very small memory buffers, which allow these companies to find all these leftover CPUs that sit on nodes with cores, but not enough memory. We now can use these cores much better. And second, with the bulk of data hosted by PM rather than DM, the crash recovery and migration will be much faster. But to do this, we have to handle 2 challenges. First one is that the PM has pretty low write bandwidth compared to read. As you can see from this chart, the write bandwidth can saturate much earlier and also at a much lower level than read. And to handle PM disaggregation in cloud-native databases, we do have to do a lot of writes, especially if the application is write-intensive. We have to flush a lot of logs as well as dirty pages. The second challenge is that we need to use CPU in a lot of things for these remote PM nodes, right? We have to do cross-node coordination when we need to interact with multiple compute nodes as well as replica PM nodes. Okay, and then to apply these logs flushed to these PMNs, we also need to burn CPU cycles in apply. Okay, and this is a typical thing you will see, the impact of CPU core allocation on performance. if we want to get performance, we have to use a lot of CPU cores. That kind of defeats the purpose of having one or a few PMN nodes to serve many compute nodes as allowed by the storage density, right? If we have a lot of space, but yet each application will cost us 10 cores, then we still cannot afford it. So this is our design, PilotDB, which has compute nodes and the PM nodes that tackle these two major challenges. So first of all, everything is centered around a new log organization called CD log, compute node-driven logs. And based on this log design, we can actually design the PMN-side to be data-heavy yet compute-light. And the storage layer is using mature technology. So in this work, we focus on the first two layers. First, on the compute side, I'm going to just talk about the CD log design. There are several things to note about it. First of all, to reduce bandwidth usage, we adopt a physical log at mini-page granularity so that we don't have to flush the entire page when we just make a small modification. And then we design the metadata so that the compute node side has almost all the knowledge needed to access data at the PM side. Especially, we have the remote page address. And finally, to make better use of RDMA, we batch our write. And at the PMN side, we have two major data structures. One is the CD log store, which are basically two ring buffers, log-free, that allow us to do high-speed WL flushing. Okay? And finally, the big bulk data storage is a RBP, remote buffer pool, which is a large pool that holds both the page data and the metadata. And because the logs are designed to be physical, our log application is now very simple and fast memory copy. Another thing, a crucial decision we make in our design is that we try to maximize the use of one-sided RDMA whenever possible. We have found that despite recent improvement, RPC implementations still cost very high latency compared to RDMA. And among the RDMA options, one-sided RDMA offers not only the lowest latency, but also consumes almost zero CPU cycles. Therefore, the majority of our data operations is done by one-sided RDMA. And that is a design decision that finally allows the PMN side to be truly compute light. One example is this remote page read, because we have large and fast RBP sitting there. We will have to read data from this buffer by the CNs. This buffer is large and fast, but when we read data page could be stale because the log application has not catched up with it, right? So existing memory disaggregation systems will apply a check at the remote memory side. But to do this, it will involve expensive RPCs. And for us, we decide instead to perform optimistic data read from the compute nodes. We read the data and do the comparison because the compute node side knows everything, all the addresses at the remote side. We can simply compare two serial numbers to see whether the page is stale. Because our physical log application is simple memory copy, in most cases, we actually can get the identical numbers and the page is okay. In the rare case where there is a discrepancy, rather than waiting for the remote log application to catch up, we actually pull the log entries from the PM side by the compute nodes and do a local application to the stale page. So evaluation, I'm going to just highlight the overall performance with SvsBench. Here we compare 4 systems. The MySQL IDEO is a system that actually has everything local. Unlimited memory, for example, okay, large enough to host our data, and then we have PM attached locally for fast persistence. LegoBase is a system published in VLDB 2021, where we have local 10 gigabyte LBP with 100 gigabyte remote DRAM. Lego PM is similar, but with remote PM. And finally, PilotDB, our system, with 10 GB local and 100 GB remote PM buffers. And we compare 3 workloads. As expected, PilotDB makes the hugest difference when we have write-intensive applications. And in this case, we actually can achieve about 97% of the performance of the ideal case, where everything is hosted local. And we achieve at least 50% improvement over the other baselines. And even with the read cases, we can achieve about 90% of the ideal performance. And for CPU and bandwidth savings, here we have even more dramatic results. Look at the left figure, where PilotDB is the blue line, and we have Lego PM as the white curve. The orange one is a system that is similar to PilotDB, but we use RPC instead. Here, the other 2 systems will require 8 or 16 cores to reach their peak throughput. Well, PilotDB can do that with only 1 core. And bandwidth, we have similar savings, and you can see the details in the paper. Finally, we'd like to close on a note on cost effectiveness. We have seen that while designed carefully, PM disaggregation can improve resource utilization and deliver good performance. But what about cost? We have a detailed analysis in the paper, and here this figure highlights the throughput per dollar comparison between the systems. And again, PilotDB, even with the more expensive processor cost factored in, still offers a much better value for dollar. And we argue that this is the reason that companies like Alibaba are actually interested in exploring this solution in the first place. Although Intel has decided to discontinue this Optane product line, we believe that similar systems, hardware offerings in the future will play an active role in cloud-native databases. That's all. Thank you.